In the last video that I made on Apollonius' treatise on conic sections, I went through some propositions relating to diameters of conic sections, and I focused on the parabola in that video just to give a bit of an idea of what Apollonius does in his book. But similar propositions are given by Apollonius relating to the central conic sections, so ellipse and hyperbola as well. Now I just want to point out now some of the implications of some of those propositions, 16 to 23 in Heath's translation. And the reason that I've left it till now, rather than included it in the last video, is because it kind of covers, it touches on what I'm wanting to cover in this video. From amongst those results of proposition 16 to 23, it follows that for any parabola, any line parallel to the axis of the parabola is itself a diameter. So this is proposition 20 from the last video that I made. Similarly, for the ellipse and the hyperbola, any line passing through the centre of the ellipse or the hyperbola is also going to be a diameter. And in the case of the parabola, ellipse and hyperbola, the series of chords which the diameter bisects is going to be the chords that are parallel to the tangent line at the point of intersection between the diameter and the section. In the case of the double-branched hyperbola, it's where the diameter will intersect the conjugate hyperbola, so the tangent line at that point, which I'll say more about later on in this video. So these theorems, to a certain extent, give a certain way of constructing diameters and chords that these diameters bisect. And this is significant because when it comes to ancient Greek geometry, it's not sufficient much of the time to merely show that something exists indirectly. We need to show that it can be constructed. And this is in quite stark contrast to modern geometry and mathematics, where the existence of certain mathematical or geometrical objects can be inferred indirectly without actually constructing the object. What is meant by a construction can mean various things in different circumstances, but in modern day existence proofs, a lot of modern day existence proofs are non-constructive. And this would be especially true if the axiom of choice is involved in a proof. So for example, the proof that every vector space has a basis. If the vector space is finite dimensional, it's not so much of a problem. It's easy to show that it's got a basis. If it's an infinite dimensional vector space, probably the axiom of choice is going to come in. It's going to be a non-constructive proof that that vector space has a basis. To the ancient Greeks, the existence of something was often shown through means of a construction. And that's what we move on to in this video, how to construct conic sections which are required to have certain properties, given certain information about them. We're not just hacking away at cones anymore now. We're given information, specific information, and we've got to construct the conic section that fits that information. So we've got to be quite delicate about this. Some really interesting stuff starts at around proposition 24 in Heath's translation, where we learn how to construct these sections given certain bits of information about them. These propositions do much more than might be realised at first, as I'm going to explain later. But Apollonius deals with the case of the parabola, the hyperbola and the ellipse separately, and the information that we're given is the length of the parameter, a line which is to be the diameter of the section, and the angle that the diameter makes with its ordinates. And in each case, Apollonius considers the case first where the diameter is actually the axis or an axis of the section, in which case the chords are going to be perpendicular to that axis. And then secondly, he uses that case to move on to the more general case where the diameter actually it's a more general diameter, and it makes an angle with the ordinates that is not necessarily, well, it's not going to be 90 degrees. So that's what we're going to move on to now. In this lot of propositions, what we're interested in doing is showing that we can reconstruct conic sections given certain information about them. So the information that we're given is, we're given a line that we want to be the diameter of the section. We are given the angle that the diameter makes with its ordinates, so the chords that it bisects, and we're given the parameter of the section with reference to that particular diameter. So I'm going to be concentrating on the parabola. A lot of what I've done up to now is focused really on specifically on the parabola. So I'm going to continue down that road, although in Apollonius's work, corresponding propositions are proved in relation to the ellipse and the hyperbola as well, but I'm just going to concentrate on the parabola. And this is going to happen in two separate stages. So first off, we're going to look at when the angle between the diameter and its ordinates is 90 degrees. In other words, the diameter in that case is actually going to be the axis of the parabola. And then that gives us a bit of a foothold really to get onto the more general case where the diameter doesn't make a 90 degree angle with its ordinates. So just thinking back to the first video that I made, if this is a parabola, then if I draw the axis of the parabola in here, so the axis is going to go through the vertex of the parabola, then the series of chords that axis bisects are going to be a series of chords that are perpendicular to that axis. So something like that. So that's the first case that we're going to look at. But more generally, and as we know from proposition 20, in a parabola, any diameter of a parabola is parallel to the axis. So let's say we've got this diameter in here, and let's say it goes to the point P on the parabola, and the chords that it bisects will be the series of chords will be parallel to the tangent line at the point P. So try and do this as best I can. Okay, so they don't bisect very well, but it's good enough. What we can see is that the angle between the diameter and the chords that it supposedly bisects is not 90 degrees in this case. So that's the second case that we're going to look at. That's the more general case. Okay, so for these propositions, you will have to use your visual imaginations a little bit, because we're going to be visualizing planes cutting through cones and all kinds of things, and there's going to be quite a few of them. In particular, we're going to be interested in the plane of the board that this diagram is drawn on. We're going to be interested in planes that are perpendicular to the board but kind of horizontal, and planes perpendicular to the board but on a bit of an angle. So obviously the planes that are perpendicular to the board that are like that and the ones that are like that, they're not perpendicular to each other, but they're both perpendicular to the board. The diagram, I'm not going to explain from the outset, so normally I explain the diagram before I actually start. In this case, I'm actually going to leave that, and the diagram will become more and more clear as we progress through the proof of this proposition. Okay, but our starting point here is this line AB. Okay, and we need to imagine this line AB as being contained in a plane that is perpendicular to the board but horizontal. So horizontal to the bottom of the whiteboard here, something like that. Okay, so also one bit of it, that's what we want to be the axis, by the way, of our parabola for this first part. We're also given the length, a magnitude that represents the length of the parameter of the parabola with respect to that diameter or axis in this case. So the parameter I'm going to use a lowercase p, is a given length. So just to clarify what it is that we're trying to achieve here with this first part of this proposition, we're wanting AB, this line AB, to be the axis of the parabola that we construct, and that the parameter is going to be p. Okay, the fact that we're given the length of the parameter p is used from the outset. So what we're going to do is we're going to extend this line AB from A but away from B to form this point C over here. So that we can do this is guaranteed by Euclid's second postulate, that we can a line segment can be extended indefinitely in either direction. So we're going to say that we're going to choose C in such a way that AC is greater than a quarter P, and this choice is going to become clear in a couple of minutes why that choice has been made. And then what we're going to do is we're going to find a mean proportional between AC and P. So we're going to use S as the mean proportional. So another way of writing that is that S squared is equal to P times AC. And therefore, we can say, what can we say? That AC squared, the ratio of AC squared to S squared is equal to AC squared ratio P times AC. To find this mean proportional, by the way, this is another thing that follows from Euclid. So Euclid, book 6, proposition 13, I think, that shows how, given two magnitudes, you can find a mean proportional between the two magnitudes. So this is guaranteed. We can construct this S. This would follow, if we've got to get from here to here, this would follow from Euclid, book 5, one of the propositions. I can't remember which one off the top of my head, but it's in there somewhere. And then I can effectively cancel the ACs here. And that's going to follow from, I think, Euclid, book 6, proposition 1. So something to do with parallelograms under the same height. Something R to one another as their bases. And okay, so what's the use of this now? Well, going back to this thing here, I can say that the ratio of AC to P is going to be greater than the ratio of 1 to 4. So that follows straight from this inequality here. So therefore, AC squared to S squared is going to be greater than 1 to 4, because we know that AC squared to S squared is equal to AC, the ratio of AC to P. So that tells me that 4AC squared is not equal to, it's greater than S squared, and therefore 2AC is greater than S. We can also say, because AC and S are going to be positive magnitudes, that AC plus S is going to be greater than AC. These two together allow me now to form a triangle. So in any triangle, the sum of any two sides of the triangle, the lengths of any two sides of the triangle, must be greater than the length of the third side. So if I form a triangle such that these two lengths here are AC, and the length, the base, let's say, is S, then AC plus S is greater than AC, is guaranteed by this. AC plus S is greater than AC, again guaranteed by this. And AC plus AC, 2AC, is greater than S, which is guaranteed by this. In other words, this triangle is a possible triangle. It is something that can actually be constructed. So again, Euclid's Elements, book 1, proposition 22, I think, shows us how to, given three magnitudes, how to construct a triangle given those three magnitudes, assuming that it is a possible triangle. So let's do that. Let's construct such a triangle. So we've already got one of our sides, AC. So let's form the triangle COA such that AC is equal to AO. And OC is equal to S. Okay, and then by adding this point E up here, I can complete this parallelogram here. So OCAE is going to be a parallelogram. So it follows straight from that AC, AO are equal, then AC is also equal to OE. And OC is going to be equal to AE, both of which are equal to S. And we're going to need to use these quite a lot in a minute or two. So we've got our parallelogram formed. So what we're going to do now is we're going to describe a circle with diameter AE in a plane perpendicular to the plane of the board. Okay, so that's this red shape in here. This is the circle that we describe, and this is guaranteed by Euclid's third postulate, I think, that we can describe a circle of any fixed radius or diameter, which is what we're using in here. And then with that circle that we've just formed as the base circle and O as the apex, we're going to form a cone. So just like I showed in the first video, we've got the line OA here, which we can extend indefinitely. So we're going to rotate that around, keeping the point O fixed, rotate it around this base circle. That's going to form the surface of our cone. Okay, and moreover, because OA and OE are equal in length, then our cone is going to be a right cone. So it's going to be a right circular cone. And what else was I going to say? Oh yes, and AOE is going to be an axial triangle of that cone. So it's almost like the plane of the board is kind of slicing through. So now that we've got our cone produced, we're going to take a slice through the cone with a plane that's parallel to that base circle. So that's going to produce this section here, this red section. And because we're cutting through the cone parallel to that base circle, by what I showed in the second video, that is going to be a circular section, okay, with diameter HK. Right, so for the next part, there is going to be quite a bit of a information dump. There's a lot to consider at this stage to make the necessary deductions that we need to make. So all I can say is I apologise for that, but it is each of the parts are necessary. If you need to watch it through a few times to make sure that you've got all the information, then do so. But here goes. Okay, so the section, the plane containing the line AB, which we started with, that is perpendicular to the plane of the board, or indeed the plane of this axial triangle now, will cut through the cone that we've just produced to make this section, so this blue section in here. Okay, the plane of the circular section that we've just produced, so this circular section with diameter HK, is going to intersect that blue section at the points P and P primed. Okay, so PP primed is not in the plane of the boards. This is kind of perpendicular to the board, as we'll see in a second. So PP primed is going to be a chord of this blue section. Okay, and bearing in mind that HK, this circular section here, could have been anywhere, then PP primed is effectively an arbitrary chord, almost. It's got a certain property that we need to take into consideration in a second. the plane of the section intersects the plane of the axial triangle, or the plane of the board, in this line AB. So therefore, what I showed in the first video, this AB is going to be a diameter in that case. The intersection of the plane of the section with the axial triangle is a diameter. So what we want to show is that AB actually bisects PP primed, the chord PP primed. So let's have a look at that now. Well, the plane of the section, this blue section, intersects the plane of the base circle in a line. So two planes will intersect in a line. So I've not drawn this line on the diagram, so I don't want it to get too cluttered. But by the nature of these two planes, namely that the plane of the section and the plane of the base circle are perpendicular to the plane of the axial triangle, then this line of intersection is also going to be perpendicular to the axial triangle. Okay, so therefore, because this plane that we cut this circle from is parallel to the base circle, then PP primed is going to be parallel to that line of intersection between the line of the section and between the plane of the section and the plane of the base circle. So therefore, PP primed is also going to be perpendicular to the axial triangle. So therefore, by what I showed in the first video, PP primed is going to be bisected by the line AB. So it's going to be bisected at the point N. And finally, because the cone that we produced is a right cone, then any diameter is actually going to be an axis. So AB is an axis, so not only does it bisect PP primed, it bisects PP primed at N right angles. So therefore, all of these little bits of information point to the conclusion that AB is in fact an axis of this blue section in here. We still don't know that it's a parabola yet. Evidence is pointing in that direction because with these being parallelograms, AB is going to be parallel to OH. So it would suggest that this is going to be a parabola. We're not quite there yet, but whatever the section is, we know that AB is going to be an axis. So we want AB to be an axis. We've got that sorted out. So we just need to show now that P is the parameter of the section with respect to that diameter. So let's have a look at that now. So going back to this up here, namely that AC to S is equal to S to P. Remember, S was a mean proportional between AC and P. Well, S is equal to AE. And AC is equal to AO. So therefore, AE is actually a mean proportional between AO and P. So, namely, we get AE squared is equal to P times AO. And therefore, AE squared ratio AO squared is equal to P times AO ratio AO squared. So cancelling the unnecessary AOs in here, we get P ratio AO, and over here we're going to get AE squared ratio AO times AO is equal to OE, and this is the bit of information really that shows us that P is actually, that this is a parabola with parameter P. How? Let's have a think again back to what I showed in the second video that I made. given an axial triangle, A, B, C, and if we cut a kind of parallel to the line AC, if you will, but perpendicular to the base, then we get, I'll try and draw this as well as I can, something like that. Now if you remember, the parameter of a parabola in the first instance was defined in terms of the ratio that it makes with the lengths of the sides of the axial triangle. So in particular we had that the ratio of PL, which is the parameter PL to PA, is equal to BC squared ratio AB times AC. Okay, so BC, base of the axial triangle, ratio to the rectangle contained by the lengths of the other two sides. Well, I'm just going to modify this a little bit now. Rather than having B and C here, I'm just going to imagine our axial triangle as being here instead. So we're actually cutting through so that the vertex of the parabola really coincides with the point B. So B and P are one and the same point in this case, because this coincides more with what we've got up here. Right, so how does this compare now? Well, the base of this axial triangle, BC, is like our AE up here. Okay, so we get our BC squared. AO and OE are like the other two sides of the axial triangle, so AB and AC. P is our parameter. AO, which is this length here, is the same as my PA in this diagram here, which is the statement that we've got here. So this is how the parameter of a parabola is in the first instance defined. Everything here seems to match up perfectly well. So what this proves then is that this section is indeed a parabola, and it's got a parameter P. So that shows, this construction shows that given these certain bits of information about the section, that we can actually reconstruct the section itself. So that's the case, that's the specific case where the diameter is actually supposed to be an axis. We're going to move now on to the more general case where we consider more general diameters. Let's have a look now at the more general case of constructing a parabola given certain information about it. So in this case, the information that we're given is, we're given a line, again, that we want to be the diameter of the parabola that we construct. We're given the parameter of the parabola with respect to that diameter, and we're given the angle between the diameter is to make with the chords which it bisects, so in other words its ordinates. So the given information is the parameter, P, so just as before, this is a given length, or given magnitude, and we're also given the angle theta. So let's call it theta. So theta is the angle that the diameter makes with the ordinates. Okay, and in this case we're assuming that theta is not a right angle. Okay, so in this diagram, for the time being, we need to kind of assume that this parabola is not there. So this blue parabola that I've drawn in. So I've drawn that in because it's difficult to draw parabolas in real time while I'm making a video. So we're gonna have to pretend for the time being that it's not there. So the rest of the diagram I'm just gonna gradually explain. Our starting point is this line PM. We want PM to be the diameter. So require PM to be the diameter of our parabola. Okay, so what we're going to do is we're going to produce PM in the kind of direction away from M, from P away from M to the point F, in such a way that PF or FP is equal to a half lowercase p. Okay, so this is guaranteed by Euclid's postulates that we can do that. And what we're going to do now is we're going to draw a line through P that makes an angle of theta with FP. So theta is the given angle. Theta is the angle that we want the diameter to make with its ordinates. So we want this angle here to be theta. So this is that we can do this is guaranteed by Euclid again. Euclid's book 1 proposition 23, that we can construct a particular angle. So angle FPT is equal to theta, and then we're going to draw a line through F which is perpendicular to the line that we've just drawn, meets it in T. So this is a right angle. FTP is a right angle. Again, that's guaranteed by Euclid book 1 proposition 11, that through a point we can draw a line perpendicular to another line. So we've got our nice right angle triangle FPT in here. Then through T we draw a line parallel to PM. So that's this line here. And then through P we draw a line that is perpendicular to that line that we've just drawn, meeting this new line in the point N. So Pn is perpendicular to Tn. And then this line segment Tn is bisected at the point A, so we want this to be equal to this here. Again, Euclid's book 1 proposition 10, I think, guarantees that we can bisect a line, no problems there. And we're going to draw a line through A parallel to Pn, which intersects Pm, the line Pm that we hope to be the diameter in the point E. It intersects PT in the point O, and we extend it down to the point L in such a way that AL times AN is equal to PN squared. So the length L, the length AL is determined by this. So AN is determined, PN is determined, so therefore AL is determined as well. So why would we want to choose this specific relationship? Well, let's have a look. If we now construct a parabola with axis AN and parameter AL, which is exactly what we did in the first part, we guaranteed that we could construct such a parabola, then the parabola will probably look something like this. Well now, if that's the case, if AL is the parameter, then AN and PN are the abscissa and ordinate respectively, with reference to that diameter AN. So therefore this parabola it's guaranteed to go through the point P as well, because of this specific choice of L. So our parabola goes through the point A, it also goes through the point P. Moreover, PM is a diameter. Why? Because in a parabola, any line parallel to the axis is a diameter. Well, PM is a line that is parallel to the axis, therefore it must be a diameter. So we've got a parabola with diameter PM. We've got that bit sorted out. So let's have a look now at this angle theta. We know that this line here, PT, is going to be a tangent to the parabola. So it's a tangent at P. How do we know that? So this is from proposition 12. So I mentioned proposition 12 in one of my earlier videos, because AT, the distance AT is equal to AN, and this is the ordinate of the point P, the line drawn ordinate wise to this axis, then that guarantees that it's really this that guarantees that PT is going to be a tangent line to the parabola. So this tangent line makes an angle of theta with this diameter PM. We also know from proposition 20 that I proved in the last video that I made, that the diameter at the point P will bisect all of the chords parallel to the tangent line at the point P. Well, if the tangent line at the point P makes an angle theta with the diameter PM, then so will any line parallel to that tangent line. In other words, the chords that PM bisects, this series of chords, will all make an angle theta with this diameter PM. So that's the second one. So that's proposition 20. This also follows from proposition 20. So now we've just got the last bit. We need to show that P is the parameter of this parabola with respect to the diameter PM, and then that completes the picture for us. So triangle FTP and triangle OEP are similar, because they're both right angled triangles. That's a right angle there in the triangle OEP. They both share the same angle theta, and so therefore the other angle is going to be 90 minus theta. So they're similar triangles. Okay, so the ratio OP to PE is going to be equal to the ratio of FP to PT. But FP was equal to half P. So OP to PE is equal to half P to PT. So therefore OP to PE is equal to, just doubling each of the magnitudes on this side, we get P to 2 PT. Well, this is exactly the condition that we require from proposition 22, which I proved in the last video as well. So by proposition 22, P is the parameter. At least with respect to PM. So an interesting thing to note here is that the parameter with respect to the axis, AL, is potentially different to the parameter with respect to this diameter PM. But it's proposition 22 that really concludes the whole argument. So just like with the previous case, we've shown that given certain information about a parabola, we're actually able to reconstruct that parabola from that information. And as you can see in this case as well, the first specific case where we dealt with the axis actually helped us to form this parabola in here. Without that, we really wouldn't have been able to get a strong enough foothold into the more general case. So this is quite a common theme with Apollonius's proofs of the propositions in this part of his work. Not just for the parabola, but for the ellipse and for the hyperbola, he does a similar thing, considers a very specific case where the diameter is actually an axis, and then from that point he moves on to the more general cases. So through these constructions that we've just seen for the parabola, you can see how the results of previous propositions, however obscure they might have seemed at the time, are really necessary components of the constructions. And this is quite a common thing to see in Greek geometry, even more so in Archimedes than in Apollonius, that very strange and obscure propositions are proved early on in a section, only for it to be realised much later just how important they are as part of a proof of a much more substantial result. And we're seeing that kind of thing here in Apollonius. Something which can be easily overlooked here, no particular special attention is really drawn to it, is that in each case the conic that we get is the result of a section cut from a right cone, in both cases that we've just seen here. So this means then that every section can be obtained from a right cone, and in a way we don't really even need these oblique cones that Apollonius deals with. And despite their more general nature, these oblique cones, they don't yield any additional sections that can't be obtained from right cones. And I guess this result in a way gives a justification as to why modern treatments of conic sections really only consider right cones and not really oblique cones. Obviously this result wasn't known at the time at the start of Apollonius's work, and so it could quite easily have been the case that oblique cones give rise to additional conic sections not obtainable from right cones, but that's not the case. Any diameter of a section obtained from a right cone is always going to be an axis, but having said that, Apollonius doesn't at this stage do away with the general notion of diameter. General diameters still continue to play an important role in what follows in Apollonius's work. So I've just got one more proposition from this section that I want to look at before I wrap up with this video. The last proposition that I want to look at introduces the idea of a conjugate hyperbola. This is the last proposition that I want to go through as part of this video. This is proposition 26 from Heath's translation of Apollonius's treatise, and as part of this we're going to assume the result from proposition 25. So proposition 25 is effectively the analogous result that I've just proved for the parabola, but for the hyperbola. So given certain information, namely that we're given a line that we want to be the diameter of the hyperbola, we're given the length of the parameter, and we're given the angle that the diameter makes with its ordinates. We're given that information about the hyperbola, and we can construct a hyperbola that satisfies those conditions. So we're going to assume that we're going to be able to do that. For this proposition, our start point is these two lines here, PP primed and DD primed. So the assumption is that those two lines bisect each other at any angle. It doesn't matter which angle they bisect at. And the aim is to construct two hyperbolae, one of which has PP primed as its transverse diameter, as one of its transverse diameters, and DD primed will be a conjugate diameter for that hyperbola. Not merely a conjugate diameter, but a secondary diameter, as explained in my second video on Apollonius's work. And similarly, we want to draw another hyperbola, this one in red here, such that DD primed is going to be a transverse diameter of that hyperbola, and PP primed will be a conjugate diameter, and not merely a conjugate diameter but a secondary diameter. And it's actually quite straightforward to do this. So assume for the time being that we've just basically got PP primed and DD primed drawn on the board, and they bisect each other at this point C. Well, what we're going to do is at the point P, we're going to draw a line PL of such a length that P primed times PL is equal to D primed squared. So what this means, another way of writing this would be that PP primed to D primed is equal to DD primed to PL. So in other words, DD primed is a mean proportional between PP primed and PL. And this would guarantee, if we choose PL to be such a length, that if we can get the right hyperbola, then DD primed would be a secondary diameter to PP primed. And it turns out we can do this. We can draw the line PL, which satisfies this these conditions here, since PP primed and DD primed are determined definite lengths, then that will determine the length of PL. So what we're going to do now is we've got the parameter, we've got the line that we wish to be the diameter of our hyperbola. We're going to construct a hyperbola, a double branched hyperbola, with parameter PL, transverse diameter PP primed, such that the PP primed makes an angle, such that the chords that PP primed bisects are parallel to DD primed. So that will determine an angle that PP primed has to make with those chords. So that follows from proposition 25. And in this way we get a hyperbola through P primed, such that PP primed is a transverse diameter and DD primed is going to be a secondary diameter. And okay, similarly we can play the same kind of game with DD primed. We can draw a line of length dm in such a way that D primed times dm is equal to P primed squared. So in a similar way we can say then that DD primed ratio P primed is equal to PP primed to dm. So guaranteeing that PP primed is going to be a mean proportional between DD primed and dm, and therefore again if we can find the right hyperbola, that will guarantee that PP primed is going to be a secondary diameter to DD primed. And we can do this now. We can, given this parameter DD primed, we construct a hyperbola, a double branched hyperbola, which is this red one here, such that DD primed is going to be a transverse diameter, and the chords which it bisects are going to be, we want them to be parallel to PP primed. So that determines the angle that we need between the diameter and its chords, and with parameter dm. So now the picture's complete. Once we've got these two hyperbolae that satisfy these conditions, just let's double check then. PP primed is transverse diameter here, and DD primed by this is going to be a mean proportional, and therefore DD primed is a secondary diameter. DD primed is a transverse diameter of this hyperbola here. PP primed is going to be a secondary diameter to that diameter. Such hyperbolae as have been constructed in this proposition are called conjugate hyperbolae. So that this red hyperbola here is the conjugate hyperbola to the black hyperbola, and conversely, we could say conversely as well, that the black hyperbola here is a conjugate hyperbola to the red one here. So that about wraps things up for this video. In the next video I'm going to be moving on to, it's going to be focusing more on hyperbole, at least from the outset. We're going to be looking at asymptotes and various properties of asymptotes. And we're going back to more manipulation of ratios and proportions. So just like earlier on in Apollonius's work, we're going back to those kinds of ideas. So thank you for watching this video, and I look forward to seeing you in the next video.